Primary alcohols can be oxidized to either aldehydes or carboxylic acids depending on the reaction conditions. In the case of the formation of carboxylic acids, the alcohol is first oxidized to an aldehyde, which is then oxidized further to the acid. Secondary alcohols are oxidized to ketones. Tertiary alcohols aren't oxidized, there is no reaction. Oxidation results in an increase in the oxygen to hydrogen ratio. Primary and secondary alcohols can be oxidized by a number of oxidizing agents such as copper 2 oxide, acidified potassium dichromate, Free-Henig's solution, Benedict's solution. At the same time, the black copper 2 oxide is reduced to red-brown copper metal. If a primary or secondary alcohol is warmed with acidified potassium dichromate solution, the orange colour of the dichromate ions in the solution changes to a green colour caused by chrome 3 plus ions in a reduction reaction, while the alcohol is oxidized to an aldehyde or ketone. If Tollens reagent is used, the clear solution will become silver, giving a silver mirror effect. If Benedict's or Free-Henig's solution is used, the blue solution will change to a brick red solution, indicating oxidation. Aldehydes and ketones. Aldehydes are identified with the name ending al. Ketones are identified with the name ending -one. Both of them will have a carbonyl group, a C double bonded O. In the case of an aldehyde, it will be on the end. In the case of a ketone, it will be on a carbon fastened to two of the carbons. Oxidizing agents such as Free-Henig's or Benedict's solution, acidified potassium dichromate, or Tollens will convert aldehydes to carboxylic acids. Ketones do not undergo oxidation. This fact can be used to distinguish between the two. Free-Henig's Benedict's solution is used as the oxidizing agent. The blue colour changes to brown as the copper 2 plus ions are reduced to copper plus ions. If acidified potassium dichromate solution is used, the orange colour of the dichromate changes to the green chromate ion, and if Tollens is used, we will achieve a silver mirror effect, again as reduction occurs. Oxygen diffuses into the cast of whiskies, and that will help form aldehydes. This is what will give whiskies their different flavours. Oxygen molecules interact within the structure of oil and damage its natural structure in a way that can change its odour, its taste and its safety for consumption. To help counter this, antioxidants are often added to fat-containing foods in order to retard the development of rancidity due to oxidation. Soaps. Fats and oils are esters. Soaps are produced by the hydrolysis of fats and oils and are the sodium or potassium salts of fatty acids. Hydrolysis of esters such as fats and oils produce glycerol and fatty acids. The hydrolysis is carried out using alkalis, sodium hydroxide or potassium hydroxide, as catalysts, and the fatty acids formed are changed into sodium or potassium salts, such as potassium stearate, C17H35COO K+, a water-soluble ionic salt. In solution, a soap molecule consists of a long, non-polar, hydrophobic hydrocarbon tail, e.g. C17H35 negative, readily soluble in non-polar compounds, hydrophobic, and an ionic carboxylate head, COO-, which is water-soluble hydrophilic. During cleaning, the hydrophobic tails dissolve in the droplets of oil or grease, whilst the polar head hydrophilic heads face out into the surrounding water, resulting in a bowl-like structure. The non-polar substance, such as oil and grease, are held inside the bowl and suspended in the water. Repulsion prevents the oil droplets rejoining and helps disperse the oil. Emulsions in food. An emulsion is a mixture of two or more immiscible liquids. In an emulsion, the small droplets of one liquid are dispersed in another liquid. Emulsions in food are mixtures of oil and water. These normally do not mix and will separate if left without an emulsifier. The emulsifier or emulsifying agent keeps the mixture stable and prevents the oil and water from separating into two layers. Emulsifiers can help to make a food appealing. They are used to aid in the processing of food and also to help maintain quality and freshness. Natural sources like vegetable oils and animal fats are often used to make emulsifiers. Emulsifiers are made by reacting fatty acids with glycerol to form molecules with either one fatty acid group, monoglycerides, or two fatty acid group, diglycerides, linked to the glycerol backbone. Emulsifiers are molecules that have two distinct ends. One end likes to be in water, hydrophilic, the other end likes to be in oil, hydrophobic. This means that they will coat the surface of oil droplets in an oil-water emulsion and effectively insulate the oil droplets from the water. It keeps them evenly dispersed throughout the emulsion and stops them from clumping together to form their own separate layers. Fragrances. Essential oils are concentrated extracts of volatile, non-water soluble aroma compounds from plants. Essential oils do not, as a group, have any specific chemical properties or functional groups in common. Instead, they are identified by the fact that they convey characteristic fragrances. Perfumes, cosmetic products, cleaning products, aromatherapy and food flavours are all uses for essential oils. Essential oils are generally extracted by distillation or solvent extraction or steam distillation. Many essential oils contain chemicals called terpenes. Terpenes are components in a wide variety of fruit and floral flavours and aromas. Terpenes can be oxidized in plants, producing some of the compounds responsible for the aroma of spices. Terpenes are unsaturated compounds formed from units of isoprene, 2-methyl-buta-1,3-diene, which has a molecular formula C5H8. The basic molecular formula of terpenes are multiples of that, C5H8N, where N is the number of linked isoprene units. Isoprene units may be linked together head to tail to form linear chains or may be arranged to form rings. One can consider the isoprene unit as one of nature's common building blocks. Skincare products. Ultraviolet radiation is a high-energy form of light present in sunlight. Exposure to UV light can result in molecules gaining sufficient energy for bonds to be broken. UV light is responsible for causing sunburn and contributes to aging of skin. Sunblock stops UV light entering the skin. This is done by the presence of compounds to reflect the light, oils to moisturize the skin, as well as free radical scavengers to prevent any oxidation. Free radicals are atoms or groups of atoms which have a single unpaired electron. Free radicals are highly reactive. Free radicals are formed if a bond splits evenly, each atom getting one of the two electrons. This is called homeotic fission. Homeotic fission takes place when UV light breaks bonds. Free radicals start and have three phases. First one will be initiation. UV light generates the radicals, breaking the bond. And then you have propagation. A propagation reaction involves the loss of a radical, but also the formation of another radical. The reaction now has to keep going, i.e. propagate itself. And termination. Termination involves radicals coming together to form covalent compounds. Free radical scavengers. Free radicals, and in particular oxygen-free radicals, are thought to cause cell damage. Untreated, the damage from free radicals accumulates with age, and the damage is thought to be the cause of many degenerative diseases, and is associated with many of the signs of the aging process. Free radical scavengers are molecules that will trap free radicals by reacting with them to form stable molecules and prevent chain reactions. Melatonin, vitamin E and beta-carotene are examples of natural free radical scavengers. Free radical scavengers are often added to plastics, food and cosmetics to help reduce the effect of free radicals.